Hi, today our group will be presenting about Marry Phase Shift Keying. Before we start, let's get to know the team. Our team consists of 3 members, Devashree, Kashwiin and myself Shangkari. So, what is our project about? Data communication has greatly evolved during the last few decades. These advancements were made possible by advances in digital circuitry as well as the availability and ongoing cost reductions. Analog communication was the primary mode of data transmission prior to the introduction of digital communication technologies. As the internet spreads over the world, the requirement for data to be transferred over vast distances grows. However, the main disadvantage of analog transmission is that signal quality degrades with distance. It also has a low level of security and doesn't facilitate data integration. An alternate to analog communication was provided by digital communications. Digital modulations are becoming an integral aspect of today's and tomorrow's communication technology. Despite the benefits of these systems, glass channel flaws such as noise can reduce their performance. Furthermore, data is typically transmitted using wireless channels, which are unpredictable and prone to multi-path fading. So this paper presents a short research article that presents a study of Marry Phase Shift Keying using MATLAB software. What is digital communication? Signals are the medium via which we communicate in our daily lives. In general, these signals, such as sound signals, are analog in nature. When communication over a long distance is required, analog signals are transmitted through wire utilizing several ways for successful transmission. For long-distance communications, traditional means of communication employed analog signals suffers from several losses such as distortion, noise, and other losses such as security breaches. Signals are digitized using a variety of approaches to solve these issues. The digitized signal allow for clearer and more precise transmission without loss. Listed here are some of the advantages of digital communication. As the signals are digitized, digital communication has a number of advantages over analog communication, including distortion, noise, and interference have a significantly smaller impact on digital signals since they are less influenced. Analog circuits are more difficult to develop and more expensive than digital circuits. Digital circuits also provide more flexibility in terms of hardware implementation than analog circuits. And last but not least, in digital circuits, signal processing methods such as encryption and compression are used to keep information private. This is the block diagram of digital communication system. The input source or the source of information are generally analog in nature, for example, voice signal and video signals. The source encoder is used to compress the data into minimum number of bits. This helps in effective utilization of the bandwidth. It removes the redundant bits or unnecessary excess bits, that is zeros, from the input data. The channel encoder does the coding for error correction. During the transmission of the signal, due to the noise in the channel, the signal may get altered. Hence, the channel encoder provides some redundant bits to the message data in order to provide an error-free data on the receiver side. The channel encoder plays an important role in the communication system. The signal to be transmitted is modulated here by a carrier. The signal is also converted to analog from the digital sequence in order to make it travel through the channel or medium. As for the transmitter antenna, in the field of digital communication, antennas are widely used. They either receive an electromagnetic wave and convert it to an electric signal, or an electric signal and convert it to an electromagnetic wave. The channel or a medium allows the analog signal to transmit from the transmitter end to the receiver end. For the digital demodulator, this is the first step at the receiver end. The received signal is demodulated as well as converted again from analog to digital. The signal gets reconstructed here. The channel decoder, after detecting the sequence, does some error corrections. The distortions which might occur during the transmission are corrected by adding some redundant bits. This addition of bits helps in the complete recovery of the original signal. Source decoder. The resultant signal is once again digitized by sampling and quantizing so that the pure digital output is obtained without the loss of information. The source decoder recreates the source output. As for the final part, this is the last block which converts the signal into the original physical form, which was at the input of the transmitter. It converts the electrical signal into physical output.
Hi everyone, my name is Devashree Sivakumar. Today I'm going to explain about M-Airy phase shift keying. M-Airy phase shift keying or M-PSK is a modulation where data bits select one of the M phase shifted versions of the carrier to transmit the data. Thus, the M possible waveforms all have the same amplitude and frequency but different phases. The signal of constellation consists of M equally spaced points on a circle. M-PSK is a modulation in which data bits choose between M phase shifted versions of carrier to send the data. As a result, each of the M possible waveforms has the same amplitude and frequency but a distinct phase. M evenly spaced spots on a circle make up a signal constellation. The channel bandwidth is lowered as a result of this form of transmission. Two or more quadrature carriers are sometimes utilized for modulation. Quadrature modulation is the term for this procedure. This is a block diagram for M-Airy transmitter. First, the data will send to serial to parallel converter. Then, the data will send to digital to analog converter. Lastly, sinusoidal signal source is controlled to receive the data. This is the block diagram for M-Airy receiver. Now I'm going to explain about constellation diagram. Constellation diagram or phase shift diagram is a graphic representation of a digitally modulated signal consisting of the constellation points used to assess the quality of a transmitted signal. Apart from usable data, the modulated and transmitted signal also includes interference, noise, and disturbance. This is an example of 8 PSK and 16 PSK constellation diagram.
We will show you how do we make a coding regarding to M-PSK, that is Mary PSK. That another term we call is multiple PSK modulation. So at the start we will clear all of the previous recording of or something like that. So for the message signal, for the example we will take a 64 bit number and then we will select a 16 mode. M is 16, so we will set at there. And then for data, for the random data message, so we will use a code called Randy code. So it will generate a random message information, and then the S will be the PSK mod, so it will create the modulated data. And then for the AWGN for constellation point, so this one it will create the noise regarding the noise signals. So for the SNR, in this example we will show you SNR equals to 40. SNR stands for system to noise ratio, and then R equals to AWGN with the code of S dash SNR dash measure. So it will generate a white noise. And here we will create like carrier frequency, something like that. So we put the bit rate of 10 to the power of 3, and then F equals to bit rate, and then TB equals to 1 slash bit rate, and then T is equals to 0 ratio of TB over 1000 and TB. And then for the transmitted signal waveform we will use the TX6 code, and then we will put on the general formula for the M-PSK. So we will put the general formula of the M-PSK at here, and then we will start the run. And then for the waveform of the signal we will plot 3 graphs regarding it, and then one of it will be and then another one will be a constellation diagram, so total will be 4. So when we run this program, as you can see, we will generate the constellation diagram for the how many bit was it? 64 bit 16 mode M-PSK, and then this is the example of message signal, the 16 PSK modulated signal, and the 16 PSK modulated signal with the AWGN, which is the noise included. So if you want to change like perhaps you want to change the mode, you just simply come at here. As you can see, I have typed it at here. You can change to 8, 16, 32 or 64 mode. So for example, if I put 32 and if I run it again, as you can see with the constellation diagram, we change to 32 mode. And for example, if I put 8 mode, and then if I change the number of bit at here, for example, if I put 1024 bit, so now if we run it, it will show us the 1024 number of bits with the 8 mode M-PSK here. And if you want to change the SNR, yes, you can. So let me change back to, okay, for example, I will put 64, mode will be 8, and then for the SNR, you need to remember that the higher the value of SNR, the more accurate the signal will be. And then if less SNR, that means it's a very poor signal. So for example, if I put 10, if you can see at the constellation, it will scatter around, so it's a very poor signal. And then if you see at the noise is so high. And if, for example, if I change back to 40 is the ideal value for it. You can see the precision of the waveform through the constellation diagram and the modulator signal. Very clean, very precise, so you can deliver the message signal.
MATLAB being a high-level array language with control flow statements, data structures, input or output defined functions, supported by object-oriented programming features, can be used for computation modeling and simulation projects. Thus, using this, we engineered a code to understand and study the M-PSK modulation and demodulation system. Our work is a first step in creating a user interactive interface to understand modulation techniques. So that's all from us. Thank you.